mixed joint types. So some joint are rigid, like just a traditional type of joint where the motor are directly connected to the load. But there are also some joints that are decoupled from the load by the springs. And this is the outline. First, we will look at the reason why I want to work on this, and then one slide for model, and then I will present the control design and some simulation and conclusion. So first is the model of the robot. So you see here that I have the model of a robot with mixed joint type. So some joints are just normal traditional one that where the load are directly connected to the motor. But the last joint, you see that I have some spring here, and here's the motor, and here's the load. That means that the load is decoupled from the motor by some springs. So the reason why I want to work on this is, first I want to improve the safety. There are two main ways to improve the safety. One is to improve from the mechanical design. So here I add some springs. So you can imagine that when the robot interact with the environment, it might be a human or another robot, and it might use too much force that can maybe damage the joint of the robot itself, or it can damage the objects that it is interacting with. So by adding some spring, it will reduce the risk of damaging the objects. And the second way to improve the safety is to try to impose some soft dynamic behavior to the robot. And that way is called impedance control. So in this work I use both, like mechanically design and on the software side as well. So here's the model of the robot. So the first equation is like coming from the normal robot manipulator. But when we add some decoupling, we have to add the second equation. So we have Q here is the joint position, the joint angular position, and theta is the position of the motors. Of the elastic joints only. So for example, if I have a robot with 6 joints and only 3 of them are elastic, so this vector will be 6 by 1, so this vector will be only 3 by 1. And S is the coupling matrix between the rigid joint and the elastic joint, and B is actually a constant. Diagonal constant matrix. So and the eta here is introduced so that we have some short equation. And here is the elastic joint, elastic torque between the motor and the position of the load, and K is the stiffness of the spring. And we have two control signals. One is UK, U Q. Another one is VC. VC is the control voltage of the motors. And this U here contains, first of all, is the control voltage of the rigid motors, of the rigid joint motors. And secondly, it contains the coupling torque here. So we will go to the design of the impedance control. So first I introduce a control law for joint side, and when we substitute this one into the joint dynamics, we have something like this. And because I use the M hat and the eta hat are just the estimated terms, so I have some delta 1 is the modeling error. And here we have the user, which is another control algorithm, control signal to be designed. So then we need to define the error, and this is just the Cartesian space error. So and G is the Jacobian, and in this work I consider only position error. So P is only the position of the end effector, not the orientation. So by substituting the term of Q2 dot here, we have this equation. So then we will design a the interaction behavior of the robot like this, where D is the damping, the design damping, and AD is the design stiffness. And then we design a sigma 1, which is the sliding variable. And by taking the time derivative, we have this one. Then we substitute the WD dot here by take the time derivative of this one into this equation, and then we have the E2 dot here, substitute it, and then we have this equation here, and we still have the U0 there to be designed. So we make an assumption that the modeling error is bounded by a delta 1 M, which is a like a maximum modeling error. And then we consider a control law for U0 like this, and substitute it into sigma 1 dot. Then we have this one. And notice that we still have the modeling error here. So next we consider a Lyapunov function, and containing the sliding mode control sigma, sliding variable sigma 1. So we take the time derivative, and we have this one like this. One thing to notice is that this one, sigma 1 sine of the sigma 1 is actually the norm 1 of sigma here. So that's why we have the sigma 1 square here. So then we have this equation, and here we still have the modeling error. So the next step is to design U1 such that we can dominate the modeling error. So the U1 is chosen like this, and substitute the U1 into this term. We have this inequality. Then if we choose alpha 2 to be large enough, larger than the modeling error, then we have that V1 is smaller than or equal to 0. that's only the jump side. Now we have to design a control law for the motors of the elastic joint as well. So we have this one. We will calculate it from the control signal of the elastic joint that we had just calculated from the previous step, and we divide by this one. This one should be should has a half. So then we have we choose a control law like this with another U2 here. We will design it later. Then we substitute to the dynamic equation, and we have the whole thing here is actually the modeling error. And like this, just to substitute this one, so that we have some short expression. And we also make an assumption that the modeling error is also bounded by some constant, and define a error for the tracking error for the motor of the elastic joint, and by that we find another sliding variable. So we also take the time derivative of sigma 2. Then we choose the U2 like this with another U3 that we will decide later to deal with the modeling error. So we choose another Gravdahl function containing V1 with and sigma 2, and here we use the same principle that this one multiplied with the sine of itself is actually norm 1. So here is norm 1 square. So again, when we choose U3, so now we need to choose U3 to deal with the modeling error. So like this. Yeah. Then when we choose alpha 4 large enough, then we will have V2 dot is smaller than or equal to 0, which means that the system is stable. So next we will go to the simulation. We will simulate the system in two cases. One is here's the initial position, and here is the end effector, and here is the desired position of the end effector. So when the robot moves without any obstacle, it will converge to the desired position. But when we have some obstacle in between, it will hit the obstacle, and then it will deviate a bit, but it will not try to push further. Like actually, it will try to push a bit, but not too much, because we have the impedance control, like a dynamic behavior imposed to the robot already. So here is in the free space. So here is the sigma 1 and sigma 2. And here is the position of the end effector. Here the error is small, just 10 to the power of minus 4. And here is in when there is an obstacle. So you see that at the end we have some steady state error, because the robot will not move further. And here it is back and forth a bit, but after all it will converge to the desired position here. And the spike here, and here as well, it indicates when the robot hit the obstacle. So conclusion is I have designed an impedance control for the robot and also simulated. So the future work is first is to implement on the real robot that I introduced in the first slide, and another step is to combine Cartesian space and joint space. This means that because now I'm working in Cartesian space, but one problem with this one is that although the end effector can converge to the design point, but for a long time, like when I simulate in like 30 seconds, the other joint will move around like this, although the end effector still stick to the endpoint, but because I don't have any term in the Lyapunov function for the joint, so the robot actually moves like this. So the next step is to do this. Actually, I have one paper accepted for this one in IROS, where I separate the like I define a bound, a bone around the end effector position, and when the robot enter the ball, it will switch to joint space to keep the robot at the end effector and also keep the pulse of the robot. And one more step is to design a algorithm without using the Proc sensor to reduce the cost. So that's the end of my presentation.